Welcome to my channel, Alchemist Class with Mr. Vishaka. And today I'm going to discuss about the hydrogen bonding. Where often there are questions in this day Edexcel as well as Cambridge curriculum class papers, and it is most vital part in this day in the chemistry course of any examination for advanced level. So the hydrogen bonding, there are lots of occasions I have came across that students make mistakes in understanding as well as to answering questions. We'll see what are the hydrogen bonding and how does it affect the physical properties of compounds in which the hydrogen bonding present. Now we move on to our video. Hydrogen bonding is common for compounds as well as molecules which contains the most electronegative element of either oxygen or nitrogen as well as the fluorine. So when one of these elements attached to the hydrogen atoms directly, this is the condition for the existence of hydrogen bonding. Oxygen atom contain two lone pairs of electrons where the nitrogen has only one, but fluorine has three lone pairs of electrons. Our basic condition is most electronegative one of these elements, either oxygen or nitrogen or fluorine, should be directly attached to. In that context, so if you have the aldehydes where the carbonyl group and the hydrogen is attached to, so these compounds do not form hydrogen bonding because hydrogen is not directly attached to oxygen atom. Here it is the hydrogen is attached to the carbon atom. So in that context, this compound does not contain hydrogen bonding between its molecules. So this fundamental phenomenon should be understood very clearly. It is that very basic thing is the hydrogen atom should be directly attached to one of the most electronegative element of either oxygen, nitrogen or fluorine. This is the condition. All these three molecules are fulfilled our basic condition that oxygen, nitrogen or fluorine directly attached to hydrogen atom. Also, this nitrogen has one lone pair, fluorine has three lone pairs of electrons, where oxygen contains two lone pairs of electrons. We'll see now how the hydrogen bonding arises between ammonia, between water as well as between hydrogen fluoride molecules. It's drawn two molecules of water here, two molecules of ammonia, two molecules of HF. You can see there will be the lone pairs of electrons as well as now this delta positive hydrogen is being attracted by this lone pair of electrons on this slightly negative oxygen because oxygen is more electronegative. So this bond should be exactly, this is the 180 is the bond angle and it is this would be hydrogen atom should be directly attached. So this hydrogen delta positive being attracted by this lone pair of electrons on this slightly negative oxygen. So it is the lone pair here being attracted with this slightly positive hydrogen which gives this hydrogen bonding with 181 angle. So it should be very accurately drawn diagram where you should show the partial charges, lone pairs on electrons as well as is a dotted line to show this hydrogen bonding. So between the ammonia molecules again, this is slightly positive hydrogen being attracted by slightly negative nitrogen because this is that attraction is happening through this the lone pair, making this one angle should be 180. There would be slightly negative charge on nitrogen again because of that high electronegativity is on nitrogen. At the same time can be drawn with that as well with the HF molecules. So it is that exactly this is the dotted line should be present where it is slightly positive hydrogen being attracted to lone pair of electrons goes in this 180 is the bond angle. So you have seen on this the past paper questions they ask you to draw two molecules of either water, ammonia, or HF, or sometimes the alcohols or carboxylic acids, where they do produce the hydrogen bonding again because our condition is fulfilled. I move on to certain other examples, but before that, I just gave you the most basic molecules which produce hydrogen bonding between them. So, out of this ray, you can see highest electronegativity on fluorine, where it is the oxygen 3.5, the nitrogen is 3.0. So, the strength of hydrogen bonding is highest. We are referring to the strength of the hydrogen bonding highest with HF, then water, and then ammonia, because it is that the stronger hydrogen bonds are produced between HF molecules. But HF is a gas, but water is a liquid, ammonia is a gas at room temperature. So you can see why water is a liquid even though it's not the strongest hydrogen bonding. This is we are referring to strength of hydrogen bonding. Strength is highest with this. Between HF, the hydrogen bonding created are the strongest because fluorine has the highest electronegativity. So you may wonder why it is then water become a liquid at room temperature but the other two become gases. So the answer lies there because the water can produce four hydrogen bonds per molecule where the others are having less numbers. Because this way water can be used two hydrogen atoms and the two lone pairs on oxygen. Altogether it can produce four hydrogen bonds per molecule and this HF can form only one hydrogen bond. Ammonia can be produce maximum two hydrogen bonds because this hydrogen can be used to form hydrogen bond. So it is lots of hydrogen bonds are present between water molecules which cause that water to be present as a liquid at room temperature because lots of heat energy is needed to overcome those. So its the boiling temperature of the water become highest out of these three compared to ammonia, water as well as HF. But sometimes the questions ask in the strength of hydrogen bonding and the number of hydrogen bonding. So those are two different types. So your answer also should be different. So the boiling points values are in the order of increasing of this nature. The void has the highest boiling point and the methane. I just got another example where it's a non-polar molecule, doesn't produce hydrogen bonding but can be compared. You have seen in questions where this kind of questions where it is four different molecules are compared with their boiling points. To explain the difference in boiling points, we can talk about all these four molecules are having almost the same molar mass, but the most significant rate is they almost the same number of electrons. They do contain 10 electrons in methane, 10 electrons in ammonia, 10 electrons in HF because here carbon 6 plus 4 hydrogen it became 10 and the nitrogen 7 electron plus 3 from 3 hydrogen make it 10 and the fluorine would be having this is that the 9 electron plus 1 from hydrogen making it total 10 electrons where it concern the water oxygen 8 plus 2 it gives you the total of 10 electrons. The relationship is with the number of electrons is the amount of the weakest interaction London forces or instantaneous dipole induced dipole interactions are same for all these molecules. Then the difference in their boiling point where the water has the highest next HF and the next ammonia and the least with this the methane answer lies here. Methane has only London forces, which is the weakest intermolecular force. So the methane has outstanding the least value when it is boiling point. Highest is with the water because it's again the same amount of the London forces, but it has hydrogen bonding between molecules, but highest number of hydrogen bonding are present between water molecules which make a lot of heat energy is needed to overcome them. So obviously, water has the highest boiling point. And the next would be the strongest hydrogen bonding between HF molecules, which shows that HF to have the second highest boiling point, and ammonia is the least out of these three. The three substances which form hydrogen bonding out of that ammonia, because nitrogen has the least electronegativity, strength of the hydrogen bonding least with ammonia. Therefore, these three would be in this order, and the methane being the last because it doesn't have hydrogen bonding. It forms the strongest intermolecular forces, the London forces, which is the weakest intermolecular force. I hope you understood the comparison of these molecules. If there is a question how to arrange molecules with the number of electrons and the relationship between the number of electrons and London forces, as well as the molar mass, also give an information regarding the amount of the electrons which are present in the molecules. So you can use to compare that. If it is a physical property such as boiling point can be compared. Next, we will see the solubility of these different compounds. To concern the hydrogen bonding in the solubility, I have taken three examples in which all three substances is the water present in three different mixtures. I have taken three different mixtures: water and the ethanol, water and the hexane, as well as water and the sodium chloride. With your basic knowledge, you know that water in sodium chloride is water soluble, ethanol is soluble in water, but hexane is not soluble in water. So this produces two different layers. Instead of hexane, you can get some gasoline. Small quantity of the gasoline can be added into water. You can see it is not mixing, so these are immiscible or is not dissolved in. We see the reasons for these two to get dissolved and why not the hexane dissolved in water. I have taken the mixture number one, sodium chloride, and the water. You can see the oxygen is having greater electronegativity. So in the water molecules, the two lone pairs are here. At the same time, it is having the slightly negative and the slightly positive charge separation occurs in water molecules. So there are two lone pairs. At the same time, the charge separation occurs because of that electronegativity difference. You can see this charge separation in water molecules that arise due to this electronegativity difference. Apart from that, there would be the attraction of these negative electrons with this slightly positive sodium. This we call this ion dipole interactions. So these ion dipole interactions are present between any ionic compound when it is referring to any ionic compound. Ion dipole interaction making those the oppositely charged ions in the ionic compound to be separated and mixed with the water molecules with the opposite charges. So often it is the soluble. And here this is the chloride ion, so it's negatively charged being attracted by these positively charged ions. Again, these are ion dipole interactions. So this the delta positive charge of this hydrogen is now attracted by this kind of this negative ion, so that the ions are fully separated and there is no way of mixing the ions to produce unless we heat it up and remove all the water. So then again this Na plus and the Cl minus would be joining. So here this the water molecules, the oxygen contain highly negative charge because it has the greater electronegativity. So in that context, you can understand why salts are soluble in water through ion dipole interactions. In mixtures of this nature, it is the ion dipole interactions are created, therefore compounds are soluble in water if they can produce bond formation, it release a lot of energy. Then to break up this, the attractions between this Na plus Cl minus ions, obvious the compound is water soluble. Ethanol is soluble in water because there will be the lone pairs of electrons on this the water molecules, where this the oxygen gain tiny negative charge, where the hydrogen gain tiny positive charge. After this, these been attracted together through the hydrogen bonding. So we call these are the hydrogen bonds. Hydrogen bonds can be produced between the ethanol and the water molecules because they in both these molecules the condition of hydrogen is directly attached to the oxygen. So in the water molecule also this phenomenon is completed. Therefore hydrogen is directly attached to the one of the electronegative elements such as this the oxygen. So here obviously there are hydrogen bonds. When ethanol is added to water, they can extend the hydrogen bonding between the water and the ethanol molecules. Therefore, ethanol such as molecules are water soluble because our condition is fulfilled. We move on to the example, the mixtures 3 and say why hexane is insoluble in water. I have taken the mixture 3 which is hexane and water. They remain insoluble. They are not mixing with each other. Main concern is the strongest intermolecular force of hydrogen bonding is present between water molecules. But the between hexane molecules are also holding together by very weak, it's the London forces. So instantaneous dipole induced dipole interactions, those are much weaker. They are unable to disrupt the strong hydrogen bonding in water, so that water molecules cling to each other and stay separately, while hexane also cling to each other and stay separately. So if you add this the hexane and the water separately into one common beaker, and then you can notice there would be two different layers are created. So the upper layer would be that less dense layer which is the hexane, and the bottom layer would be the water because it is now higher density layer. So they do arrange inside a common container. It is depending on their density difference. So this lighter one will be floating on the heavier one. So it is hexane would be the upper layer and water become the bottom layer. So it is unable. The main concern is that the hexane, between hexane molecules, there are weak intermolecular forces, which are the London forces. So instantaneous dipole-induced dipole interactions, which is unable to disrupt the strong hydrogen bonding present in water. So these are remaining separately as two different layers in a common container. I hope you understood the hydrogen bonding and it is the effects on the physical properties of compounds with the boiling point of compound as well as the solubility. Thank you so much for watching the video. Hope to meet up you soon with another video. Thank you.